Okay. Now let us move now to Luis Fernando Elizondo's presentation. As it happened, we had some little accident in our physics institute, and Luis will actually use my own computer and my computer. So let me just mention that his talk he will present it from my screen. So even if you see my name, it will, from now on, it will be Luis. So
and I apologize for the inconvenience. We had some trouble.
That's okay. That's okay.
And I had to run here to be able to present some work. And
it's here, but how to share the screen?
Yeah. No, but you are not sharing the screen. Oh, where is it? You need to approve this. Where is the presentation?
It's probably behind it.
Perhaps here.
No, wait. Yeah, there it is.
Thank you. What is it? Okay. So I guess everyone is now looking at my screen. Can you? Oh. So can anyone confirm if you are looking? Please confirm if you are looking at my screen.
So. Yes, we can look.
Yes.
Your
okay.
screen.
So I'm very sorry for the delay and for all the accidents. But anyway, this was supposed to be, let's say, a friend. We are supposed to have an open and friendly atmosphere to organize discussions and to identify problems according to the scope of the conference. I hope this helps to make it more friendly, less formal. And I want to thank, as part of the organizing people working on this, to the participants, to Jan, to Marco, and to Fernando. And I hope this truly will help us to establish this kind of collaboration and discussions and so on. It is somehow weird because this was more or less an experimental roundtable, and I'm the only one being an experimentalist here. But of course, as a theoretician, I took a lot of, let's say, challenges to be addressed from a theoretical perspective. From writing, even though Jan already addressed many of his own problems, I think there are open issues there. And also, as we already established with the work of Fernando, and more crucially with Marco, he, for instance, emphasized a lot of aspects regarding aging phenomena and so on, which many people present here, like Thomas Voigtmann, Chegos, and so on, many theoreticians would be interested. So I wanted to talk, and I also wanted, since we are quite late or delayed, I wanted to, or I shortened my talk to only emphasize, or let's say, we already looked for challenges, fundamental challenges for us, the theoreticians, from the experimental point of view. But I would say that there are also challenges for the experimentalists from some predictions of the theoreticians, and this is more or less what I wanted to discuss. And since I knew that Marco was meant to describe some very interesting results on mixtures of colloidal particles and non-equilibrium states, I wanted to talk about that. So in particular, I wanted to talk about colloidal mixtures, which more or less allow for the tuning of the properties of many amorphous solid materials upon the modification of composition, size ratio, and so on. And I just put it here, 3 well-known examples, and I will refer to 2. The first of which, it was introduced by Marco, and he already emphasized the amount of, let's say, technical and fundamental problems in providing measurements, accurate measurements for the dynamics and the structural properties of this kind of systems. I'm talking about highly asymmetric binary mixtures. And I will also pose some challenges for the description of slow dynamics and non-equilibrium behavior as observed in slowing down of the dynamics and non-equilibrium behavior in colloid polymer mixtures. But there are other examples of mixtures which are also relevant and might be of interest, such as metallic alloys based on zirconium, which also allow to produce glassy states with very fascinating and interesting important properties. So from the theoretical perspective, we know that there are, among other, two theories which might be very well appreciated for the audience. Thinking that people like Thomas Feynman, Shego Shannon, and Magdaleno, and all his group, Pedro Ramirez, and so on. And I'm talking about the self-consistent generalized Langevin equation theory, which is one of the possible approaches for the description of glassy states in mixtures, especially in binary mixtures and also in colloid polymer mixtures. And or alternatively, we can also apply the mode coupling theory, or refer to the mode coupling theory, which also provided very nice predictions for the understanding of experimental characterization for the non-equilibrium states of mixtures. These are a couple of examples of the characterization of distinct glassy states that fortunately Marco already introduced in the case of a binary mixture, as he probably emphasized, because I missed much of Marco's talk to be able to come here. There are two types of glass transitions in both systems, or many, but at least qualitatively two that we have explored combining mode coupling theory or the self-consistent generalized Langevin equation theory with experiments and simulations, which I will summarize very briefly to show these challenges. So just a small commercial, both theories can actually be merged in just one, let's say, theoretical description, which gladly allows to transfer knowledge from one theory to the other. They can, upon the let's say, the proper recognition of writing variables for a mixture, one can realize that actually both theories are more or less slightly different descriptions of the same underlying physical laws of non-equilibrium dynamics. So, and what we have been doing during the last years is to build a bridge to allow to transfer knowledge from one theory to the other. For instance, some of the elements of the non-equilibrium extension of the Langevin approach can be now integrated to the mode coupling theory or inspired, let's say, non-equilibrium versions of the mode coupling theory, as I think Thomas Feynman will present in our next session. But also, one can also merge the non-equilibrium self-consistent generalized Langevin equation theory with further extensions of MCT. For instance, MCT, the work that probably Tommaso Rizzo will introduce in our next session concerns to the merging of the mode coupling theory with the beta relaxation theory, allowing to characterize let's say, descriptions beyond the mean field theory and so on. And this will be discussed in our next session. But I just wanted to emphasize that both descriptions, which allow for a very nice characterization of these glassy states, can be merged. And this is actually the topic of our next roundtable regarding the construction of unified views for the theoretical description of the glass transition. So let me summarize very, very briefly what is the physics of this system that Marco introduced already, which is, let's say, can be more or less easily summarized by this non-equilibrium states diagram, which considers in each of these axes the concentration of a small and big particles for a binary mixture of colloidal particles with a high degree of asymmetry, let's say 1 to 5 in sizes. So for this kind of system, or for even larger asymmetry, one can recognize experimentally two types of glasses, one of which is formed by a tremendous amount of big particles, in which the small particles can still diffuse, and this is called the single glass. I guess that Marco already introduced some of the features of that kind of glass. But upon the exchange of small and big particles, one can also form a different kind of glass with different physical properties, which is conformed by a majority of small particles, which have slow dynamics, and which more or less slave the big particles. So the big particles become slow because the majority of small particles are becoming a glass. And we actually characterized combining the techniques that Marco was describing before I got without the internet, but also combining extensive numerical simulations based on molecular dynamics. We characterized, for instance, how does the transition approaching a single glass state looks. And one can compute, for instance, the collective dynamics and the self-dynamics of this system approaching this transition to recognize that there are different patterns. For instance, that the collective dynamics of the whole system becomes coupled, and both species undergo, in terms of their own relaxation times, a slowing down, as described by the intermediate scattering function corresponding to each species, which can be resolved, as Marco, I hope, explained. But also there is a dynamical decoupling of the big and small particles relaxation times in terms of the, let's say, self-intermediate scattering function of properties such as the mean square displacement, which allowed for the characterization of the localization length. And then one can also access to relaxation times, just as Marco presented for all the other system that he was characterizing, to notice coupling or decoupling depending to which state one approaches. For instance, if one looks at the correlation functions of the small particles, which are these empty symbols, and the big particles in both simulations and theory, one finds that approaching this single glass state, such dynamics, the self-dynamics becomes decoupled. This is observed in these dark black symbols and empty and filled symbols, which are the results of simulations, and the theory describes more or less the evolution of those relaxation times by the theory. But one can also explore different length scales and observe that the evolution of the collective relaxation times along this transition follows, let's say, oscillations which are mediated by the structural factor, which is, as I will show immediately, different as observed by approaching this other transition. We characterize actually that transition, which is quite difficult in both experiments and simulations, because that requires to resolve the dynamics of a lot of small particles. And I can't say about the complications in the experiments, but I can tell that that makes extremely difficult to explore these states close to this transition in simulations. And one immediately recognizes different patterns for the relaxation of both the collective relaxation times, but also the self-correlation times, which become, let's say, correlated and both increase simultaneously, describing this effect of that, let's say, this physical scenario in which the small particles slave the big particles. So once we have characterized this system, I want to emphasize that we use these two theories that I was referring, the mode coupling theory and the Langevin approach, through many years to characterize these features of a glassy system. But these theories are, as many of you know, or all of you know, have a severe limitation, which is they are more or less, there are theories to understand non-equilibrium phenomena, but based or relying on equilibrium objects. And one of the main, let's say, fingerprints of any glassy state is aging. So there is an open problem to describe this kind of transitions from a fully non-equilibrium perspective, and there's a lot of information, experimentally speaking, that confirms that approaching the glass transition in binary mixtures, which actually do not have so large asymmetry, so there is not even the existence of a single glass or a double glass. But even in those conditions, there are enough experimental data that confirms that the dynamical quantities of both species evolve with the time of observation. And one would like to describe then this kind of transitions from a full non-equilibrium perspective, which already poses a new challenge for experimentalists, for people making simulation, and of course for the theoretical description of these systems, which is describing these experimental facts. The fact that when one compresses the system to reach a glass transition, the mean square displacement evolves with time and develops these characteristic plateaus of the glassy state. And at the same time, the fact that variables as the collective alpha relaxation time also evolves and becomes larger with waiting time, thus defining, let's say, non-equilibrium relaxation law for the collective dynamics. And this is an open challenge to be addressed. And I think we can, I mean, there are not fundamental barriers in my perspective to address this problem from let's say, using the non-equilibrium version of this theory for colloidal mixtures. But of course, there are a lot of technical details and a lot of work to be done. But then there are some remaining challenges to be addressed in the understanding of these binary classes of hard spheres. And one of them refers to the characterization of aging phenomena along both transitions. Even more interesting aspect of this, the study of this phenomena and so on, it's the possibility, I mean, using fully non-equilibrium approaches to understand the influence of the protocol of fabrication of one of these two glassy states on the resulting relaxation laws for the dynamics during aging. For instance, when one approaches either this transition from the fluid state to a double glass or from the fluid state to a single glass, the theory predicts, let's say, Marco was emphasizing, for instance, the importance of the kinetics of let's say, structural properties or properties associated to the structure of the system with waiting time. And as it happens, the theory predicts different structural evolution for a binary mixture approaching these transitions upon quenches, for instance, and predicts different kinetics at the structural level for the system approaching each of these states by different routes. And without solving the equations, one can realize that this might lead to different relaxation laws for the aging of the dynamics. And it will be very interesting to explore this problem. So this is one problem that, let's say, now the theory we can say that throws to the experimentalist. Of course, this might be extremely difficult to be investigated or even impossible. But I think I have already posed this kind of challenge to Marco, for instance, and to Ramon Castañeda, which is also here, to try to address this kind of problems for the, let's say, try to make a fully non-equilibrium characterization of this problem. Another one for which I will briefly summarize some interesting results for concerning to binary mixtures. Let's say it's related to the study of the dynamics in colloid polymer mixtures. And the results that I will show are in the following film, concerned to the predictions of the theory using the well-known as a Kurosawa representation for this kind of mixture, in which one considers typically a hard sphere mixture of colloids, which is represented here, with some polymers on the mixture. And then to represent this system, one considers hard sphere interactions between the colloids, but neglects the hard sphere interaction between polymer and polymer, and just an additional contribution, let's say, between colloid and polymer mediated by a hard sphere potential, which effectively produces an attraction between polymers, between colloids, sorry. So for this kind of representation, which also have parameters which mediate this kind of interactions, such as the degree of asymmetry and the concentration of both species, or let's say the molar distribution, the theory even the equilibrium version of the theory provides very nice theoretical predictions which have not been confirmed or disregarded. For instance, for large degree of asymmetry, it predicts some sort of topology which looks like the dynamical arrest scenario for the binary mixture. But for instance, this line in blue that we are seeing here describes the dynamical arrest of the large species, which is the colloid in this representation, and still predicts a region in this representation in which we have the polymer concentration and the colloid concentration, predicts the existence of a region in which the colloids are expected to form a glassy matrix in which the polymers can still diffuse. And upon the addition of more either colloids or polymer, there is another transition in which the polymers become arrested in this matrix of colloids. And of course, one also needs to deal with the existence of a predicted existence of a spinodal region over here, which doesn't allow to explore, let's say, for larger concentration of polymers, no? And this offers, let's say, another interesting challenge for experimentalists, because I think that it should be quite difficult to resolve the dynamics of the polymers, but at least we know that one can expect different kind of transitions for the colloids with different features at the level of localization lengths, for instance, and at the structural level as well. And of course, it is also an open challenge for both theoreticians, experimentalists, and everyone interested in to explore what happens inside this region. And here we are exploring a lot of a region of, let's say, high concentration of colloids. But what will happen if we are, let's say, at a smaller volume fraction of colloids and explore what is the effect, the dynamical effect, or the effect at the level of the dynamics on the whole mixture upon the addition of polymers? It is also an interesting problem, and I think it is related to, it might be related to many of Marco's observations regarding the attractive or the NIPAM particles with, combined with polymers. Another even more interesting prediction, in my opinion, is what the theory provides for the same mixture, but without asymmetry. The case in which one has a comparable size between colloids and polymers. And there are experimental characterizations that I will show immediately that more or less fit these kind of conditions in another region of this state space. But let's say for this kind of system, the system also, the theory also predicts the existence of two kinds of arrested states. One in which only the colloidal species arrest, but more interestingly, this region at which, for instance, if one fixes the concentration of colloidal particles upon the increase of polymers at fixed volume fraction, which is more or less a representation, of course, to higher volume fraction, but a representation of Marco's experiment on NIPAM particles, there is a transition at which the polymer is predicted to undergo dynamical arrest. And these predictions actually have been confirmed through the development of extensive molecular dynamic simulations, at which it has been observed that there is a dramatic drop of the diffusion coefficient, which is represented here by these blue symbols and lines in the theory. There is a dramatic drop of the diffusion coefficient of the polymer species, while there are essentially no changes in the diffusion coefficient of the colloidal species upon following this line. Exactly, I think this corresponds to 40% of the concentration, if I remember correctly. And this is also a very interesting prediction to be tested by experiments. Of course, it requires to resolve the dynamics of the polymers in the presence of a lot of colloids, which might present like complicated challenges from the technical perspective. But let's say this is a visualization of this kind of experiment following, as I said, this line at fixed concentration of colloidal particles. and increasing the polymer concentration. And what one observes, let's say, it's the evolution of an initial configuration in which here the colloidal particles, remember that they have the same size. Here they are, just for visualization, represented by smaller particles, just to allow to observe the initial configuration of polymers. And as the time elapses and increases, then one observes the clusterization of polymers, and they form these aggregates, and this is the source of this dynamical behavior. So characterizing experimentally and confirming the existence of these two possible states for these mixtures, it's also a very nice challenge, I would say, that it is posed by the theory. And there are trying to connect with Marco, there are also other measurements for a different kind of polymer colloid mixture, but let's say in this regime where the sizes are more or less comparable, in which let's say fixing the volume fraction of the colloidal species or confiners in this context, in the context of this problem, upon the addition of polymers, one observes a drop in the diffusion coefficient of the polymers. So that this is why I was wondering what is the influence of the polymer dynamics in Marco's experiments, and what is the connection to the, for instance, latency and delay effects that he is observing at the level of, and aging effects at the level of both structural and dynamical properties. And also very interestingly, upon the addition of polymers, these measurements also report that they more or less approach a spinodal region in which there are no further measurements and so on. But as many of you know, and probably this will be discussed in our next table, the non-equilibrium extension of the Langevin approach allows to explore what happens when one approaches and goes into these kind of spinodal regions. Although here, in the case of mixtures, this is something that we haven't explored so far, but it is also an open problem to throw to experimentalists. So we actually try to characterize this kind of measurements, and one phase is actually that let's say, a fundamental problem, that if one wants to characterize the behavior, the dynamical behavior of the polymers upon a representation using the Kurosawa model, one immediately gets mapping the experimental conditions into a hard sphere system. One gets into this spinodal region, and this is complicated because then one is forbidden to use approaches such as the equilibrium version of the Langevin approach or the mole coupling theory. So this will be also a very interesting, let's say, a project to start with someone interested. And actually, Edilio Lázaro have found that if he just forgets about the Asakura representation, and for many situations involving colloids and polymers, he just assume a hard sphere binary mixture representation, he can actually reproduce quite well the experimental facts concerning the behavior of the diffusion coefficient of the polymers. So in summary, there are some challenges to be addressed also from a, let's say, combined perspective of theory, experiments, and simulation regarding another well-known glass-forming mixture. And first of all, it's the experimental exploration of the, let's say, these two states, the two kind of, or three kind of arrested states in a colloid polymer mixture, which, as I said, hadn't been either confirmed or disregarded from an experimental point of view. It would be also interesting to discuss what is the role of the dynamics of the polymers, as I said, in determining the behavior of the colloids, which, if I remember correctly, are more or less at 10% of concentration in volume fraction, let's say. But for it is my belief that the Kurosawa model is not very convenient to understand the behavior of a mixture, of a colloid polymer mixture for small concentration, let's say below 30% of polymer, of colloids, and large concentration of polymers, where I would suppose that a lot of polymers might have a collective dynamics that can slow down upon the increase of the concentration of polymers. So I suppose that could define a very interesting problem to be addressed. And if this is the case, so another, I would say, important problem is how these dynamics of the polymers, if that were the case, it is related to the latency effects and aging behavior that Marco was discussing, and if it would be possible to characterize, for instance, using theoretical approaches and combining simulations as well, the behavior observed for the collective alpha relaxation time as a function, for instance, of many length scales of observation. And well, also the characterization of the aging effects that Marco was presenting. And well, I think this more or less summarizes what I wanted to discuss. I wanted to also present some results concerning the characterization of the process of arrested spinodal decomposition, but I think we are already extended a lot. So with this, I would like to finish.
You still have 3 more minutes.
Now, let us keep it for the discussion if there are more questions, and thanks for your attention. Thanks, Magdaleno.
Okay, thank you, Luis. Okay, let me see, how can I recover the